not a huge amount of content in this lesson. So this lesson usually would be combined with a practical, or at least demo. I don't think we do it as a class practical. I think we do it as a demo because we don't have enough equipment. So what do we need to know? Well, we know what the inverse square law is, right? Because we know that gravity, for example, is proportional to 1 over r squared, or the force of magnetism is proportional to 1 over r squared. Right, so we know quite a lot about this. We're going to be very much talking about the intensity of radiation being proportional to something over r squared. All right, so obviously we know what this means. At some distance, you have some given intensity. If you double that distance, then that intensity is going to go down by a factor of 4. And if you triple that distance, again, goes down by a factor of r squared. All right, so we know all this. Right, intensity has units of watts per meter squared, which means that intensity is equal to power over area, which I think again we know. Right, but this is useful when we're talking about radiation. Right, it's useful because then we can write it in terms of what we know about a photon. Obviously, the area of a sphere is 4 pi r squared, and power is obviously energy per second. So it's the energy of a photon times by the number of photons. Right, which is not exactly revolutionary. Okay, and then that is obviously, you know, per second. So we could times by the time, for example, the time that this occurs. Or usually this is number of photons per second. All right, so that therefore the units are fine. So we probably wouldn't put time in here. We would probably just have this as number of photons per second. So in terms of what we would do at school, you know, you can probably guess where this is going. Usually the required practical involves us having a radiation detector, which is a Geiger-Müller tube attached to a counter. And then we have a meter ruler, and then we have our radiation source. Which is gamma. Okay, and then we are simply doing a count rate versus distance. Right, so we would then fill in the tables. Right, and then that would allow us to plot a graph of distance versus either count rate, in which case it will look something like this, or it could be like the square root of the count versus distance, in which case we would expect to see something like this.
So can you move it down a bit, please? Thank you.
Right, now you might ask why it doesn't go through go through 0, 0. That's because in this practical, they are often concerned with, this would be the systematic error in the distance, right? So there'll be some error in the distance measurement, right, which is obviously going to come from the general uncertainty of measuring like plus or minus a millimeter. But it might also come from the uncertainty in this distance here. Right, we don't know exactly where this piece of radiation is being detected, so there is kind of an uncertainty here. Now, there's not that much to it. There's a couple of little bits and pieces that are useful to mention, such as when we do the count rate, we have to be really careful to make sure we don't make a silly mistake here. All right, what do we have to do over a period of time? So we would count, you know, say over a period of 1 minute, for example, and then repeats are really important because radioactive decay is random. Right, so you know you can do this a million times and you might never get the same count if the count's high, right? Because it's random. And importantly as well, you need to subtract the background count rate, right? Because if you just have a Geiger-Müller tube just in your lab, right, it will be picking up the odd piece of radiation. So that comes from a variety of sources, which you will detect. And I can't remember exactly what the count rate usually is, but it's in the region of like 10 to 20 a minute. So usually we'll have this out and we would just leave it for a period of a couple of minutes and would see the count rate. And you know, this is always nice because when you first show the students GCSE, they get really worried. You know, there's radiation all around us, where's it coming from? But of course, you know, we now know that it's just natural. So background radiation comes from loads of different places. It comes from cosmic rays, so it comes from space, which is a large proportion of the background radiation. There's naturally occurring radiation in things like food or carbon atoms, a certain percentage, like 1% or something of atoms, or 0.5%, I can't remember the exact percentage, are radioactive anyway, naturally, so we can do things like carbon dating. Obviously, there is a small amount from things like nuclear power plants, right? But this is tiny. Right? It's not something to ever be worried about. Radon gas, which comes from rocks. Again, there'll be a few counts per second. Other things like medical uses as well. You know, 1 or 2 gamma rays might escape from a hospital if it's being used, but again, this is tiny, right? It's not really something that we would need to ever worry about. Equally, like the radioactive sources that we have in our laboratory, like 1 or 2 gamma rays from them will escape and will get to even you in your house, right? But it's going to be so tiny that it's basically negligible. You know, this one here, or these two are by far the highest one. There's absolutely nothing you can do about this at all. It's just naturally occurring, but our bodies have evolved to deal with this, right? I'm going to link to 2 videos. I'll put them in the chat now, and I'll also put them in the lesson itself. And I would highly recommend, like this evening, you watch them if you haven't already seen them. A lot of you might have seen them. So the first one is the Veritasium video, which is the most radioactive places on Earth. and it's if you haven't seen it, it's really, really worth a watch, because he goes to places like Chernobyl, like Nagasaki, Trinity test site, and he talks about how radioactive these places actually are. And then he talks about background radiation. It's really, really interesting. And the other one I will find in a minute, and it's also about radiation. So the last thing I want to talk about is just, which is probably stating the absolute obvious. If I repeat this experiment with an alpha or beta source, will it follow the inverse square law? Hopefully, you can straight away say they won't follow the inverse square law. Right, and why don't they follow the inverse square law? Right, because so much alpha and a significant amount of beta is getting absorbed by the air anyway. So this inverse square law, right, and this maths here is basically a mathematical argument. We're looking at how something spreads out in space, right? But alpha and beta are absorbed by air in the way that gamma isn't. So occasionally they try and trick you and we'll give you a table of alpha and beta and just get you to realize this fact. Now, this lesson is obviously focused quite heavily on a practical. We are, of course, aware that your ability to do practicals over the past year has been very, very small. So we are aware that any questions in the exam on practicals you will find harder to answer, or you might find harder to answer, and may not be a fair reflection on your abilities. So before anyone complains, we are completely aware of that, and we will take steps to adjust for that in any mock exams. All right, so we're not going to be judging you to the same standard on practical questions as we would do in a normal year. Are there any other questions?
Sir, about practicals, if we don't have a chance like to carry them, would we still get a pass?
Yes, 100%. You will get a pass. You've all demonstrated in the fact that we have done enough skills, and obviously it's not possible for us to have done the other one, so it wouldn't be fair otherwise.
Yeah.
If we have time, we'll finish. We'll do some more practicals, but it's a big if. All right, what I'd like you to do, please, is to log on to the classroom, find the questions on the inverse square law from today's lesson, and to complete them.